Hello, and welcome back to Physics 41, University Physics 3. So before we proceed with today's lesson, let's first review some of the concepts that we need for this topic. So in the previous lesson, we have discussed about capacitors and what is capacitance. So it's basically a quantity that describes the ability of a capacitor to store electric potential energy or electric charge. And it is just the ratio of the charge stored in the plates of a capacitor divided by the potential difference between the plates of the capacitor. So from this formula, we can actually manipulate this to solve for the charge, C times V, and for the stored energy inside the capacitor, which can be any of these three equations: 1/2 CD squared, Q squared over 2C, or 1/2 Q times V. So for this lesson, we will be focusing about the different designs of a capacitor and focus mainly on the parallel plate capacitor. So without further ado, let's start the lesson. Okay, so the parallel plate capacitor is the simplest or the basic capacitor design. So we basically have two conducting plates, two metal plates, say both have area A, plate area A, and they are separated by a distance D. So that's it. You basically have a capacitor. You have two metal sheets with area A and separation distance D. So this is essentially a capacitor with nothing in between. So nothing means vacuum, no air, nothing, no thing, nothing. So the capacitance of this capacitor is given as this equation. So we will denote the capacitance of this capacitor as C sub 0 or C naught to indicate that this is a parallel plate capacitor in vacuum. And it's just equivalent to epsilon naught, the permittivity of free space, times the area over the separation distance between the plates. So again, the permittivity of free space is given by this constant value, 8.854 times 10 to the negative 12 farad per meters. So as you can see here, you will notice that the capacitance only depends on the area of the plates and the separation distance between them. Which means that the capacitance does not necessarily depend on the charge stored on the plates or the voltage between the plates. It only depends on the design or the shape. Take note, the capacitance doesn't change even if the capacitance is charged or uncharged, or even if you connect it to a battery or a potential source or not. The capacitance is still the same. It only depends. It's an innate property of a capacitor. It doesn't depend on how much voltage you put into it or how much charge stored on its plates. So it only depends on its capacity. In its essentially it's how large it is, because it's design or its shape. So there are also other capacitor designs, such as the cylindrical capacitor, which is just a parallel plate capacitor rolled into a cylinder. And the capacitance is given by this equation. L is the length of the cylindrical capacitor, and RA and RB are the inner and outer radius of your cylindrical capacitor. Similarly, for a spherical capacitor, the capacitance is given as this one. So in order to obtain this result, you first need to find the electric field of this cylindrical capacitor and this spherical capacitor, and that is done using Gauss law. And once you obtain the electric field, you can now find the potential difference between the two plates of the capacitor. And then to solve for the capacitance, you just use uh, Q over V. So if you already know the potential difference VAB, then Q over VAB is your capacitance. So take note that in the limit that the two radii rather, RA and RB are similar. So you have a very thin capacitor plates or very small distance. These capacitances will approach to that of the parallel plate capacitor or the flat capacitor. So take note, as an analogy, I will use the Earth. So the Earth is a sphere. But if you focus on only on a small part of the Earth, you will notice that these two lines almost look like two parallel plates. And the same way with the Earth. If you only focus on a small part of the Earth, of course, it looks flat. So that's the limit when the capacitance or everything, a cylindrical or spherical capacitor or any other design of capacitors always approach the parallel plate capacitor limit. So let's now have an example. So what do you think is the size of a 1 farad capacitor? So actually, if you uh, buy a capacitor in an electronics store, the capacitance values usually that they have are in nano and nano and microfarads. If they have a millifarad, then that's actually a very large capacity or large capacitance capacitor. So how about a 1 farad? So if you have a parallel plate capacitor and it has a capacitance of 1 farad and the plates are 1 millimeter, so 1 millimeter is a very small distance, 1 millimeter apart, how large is the area of the plates? Okay, so we start with this equation. So we are given with the capacitance C naught 1 farad, the distance are also given 1 millimeter, and then we need to solve for A, the area of the plates. So cross multiply and some manipulation, we get this formula for A and substitute. So the capacitance is 1 farad. The distance is 1 millimeter. So 1 millimeter, the milli prefix means divide by 1000 or times 10 to the negative 3. So 1 millimeter is, in terms of meter, is 0.001 meter. So we need to convert our units to standard units. Now, of course, this is our constant. So the farad will cancel each other out, the meter will go up, and you will have meter squared. So the answer of this is 1.13 times 10 to the 8 square meters or meters squared. That's approximately 11,300 hectares. So if that's how large a 1 farad parallel plate capacitor is, with nothing in between. So how will you separate 11,300 hectare plates with a distance of 1 millimeter with nothing, with only vacuum in between? That's actually very impossible. So nowadays, you can have 1 farad capacitors with just the size of a battery. So that's small. And the key for that is the dielectric that you place it in between. So we'll discuss about capacitors with dielectrics in the next lessons. Okay. So another example. So what happens when you change the shape of your parallel plate capacitor. So you have a parallel plate capacitor. It has a potential difference of 1.5 volts. So this is a charged capacitor. And the plates are 5 millimeters apart. And the area of the plates is 100 millimeters squared. So what is the capacitance of this capacitor? So it's just easy, right? So the capacitance of this capacitor is just epsilon naught A over D. So simple substitution. Now the key here is to convert the units. So millimeter squared. How do you convert millimeter squared into meter squared? So the key here is to use a conversion factor. The conversion factor is 1000 millimeters. That is actually your 1 meter, right? 1 meter, 1000 millimeter. There are 1000 millimeters in 1 meter. So this is your conversion factor. You multiply this in your 100 millimeters squared. But take note, we need to get rid of the millimeter squared units. So you square this one, square this one, square this one. So that is your conversion factor. So you multiply this to your area and you will get a result. So you do that and you will get a value of 1.77 times 10 to the negative 13 farads. Okay. Letter B. What happens to the capacitance when the distance between the plates is increased to 10 millimeters while keeping the area at 100 millimeters squared? So the same area, but the distance is now twice. So you will notice from this formula that the capacitance is inversely proportional to distance, and it is directly proportional to area. So meaning, if you increase the area, you're actually decreasing the capacitance. So in this case, if you double the distance, then that means the capacitance will be 1/2 divided by 2. If you triple the distance, then the capacitance will become 1/3. That's what inversely proportional means. So meaning, you use the same formula and you will find that the capacitance will now be from 1.77, it now will be 0.89. And that's actually 1/2 of the 1.77 because you double the separation distance D, making the capacitance 1/2 of the original value. Okay, letter C. What happens to the capacitance when the area is instead increased to 200 millimeters squared while keeping the separation distance at 5 millimeters? So this is now changing the area. And take note, capacitance is directly proportional to area. So meaning if you double the area, you also double the capacitance. So you use the same formula and you will actually get a value of 3.54 times 10 to the negative 13 farad, which is double 1.77 times 10 to the negative 13 farad. So we can actually verify our answers using a Phys simulation called Capacitor Lab. So this you will use this Phys simulation in your virtual laboratory for this course. So in the first problem, you have a capacitor and the capacitor has a charge of 1.5 volts and an area of 100 millimeters squared and a separation distance of 5 millimeters. So these are the initial conditions in the first problem, letter A. And you will notice that the capacitance is exactly this. We got this exact value, 1.77 times 10 to negative 13 farad. If you are further asked to solve for the charge stored on each of the plates, so Q is just capacitance times potential difference V. So you just multiply the two, this one times 1.5 volts, and you will get 2.66 times 10 to the negative 13 coulomb. And the stored energy corresponding to that is 1.99, or round off 2 times 10 to the negative 13 joules. Now, in the second problem, letter B, you actually increase the separation distance to double. So from 5, you increase it to 10. So double. So you will notice that the capacitance is 1/2, 0.89. So from 1.77, it's now 0.89 times 10 to the negative 13 farad. So that's what happens in the second example, letter B. And in the last example, letter C, so you go back to the original separation distance, but now you increase the area to double. So from 100, you get 200. I can't get 200, so round off na lang. So the exact answer actually is 3.54, but here it's 3.56 because this is not exactly double. It's 201. I can't seem to get the exact 200 millimeters squared. So that one, you also double the capacitance. So familiarize yourselves with this virtual laboratory, because you will be using this in your or familiarize yourself with this PhET simulation, because you will be using this in your virtual laboratory for this chapter. Okay. So going back, those are our answers, and okay, that's the end of the lesson. So basically, as a summary, capacitance only depends on the shape of your capacitor. So if you have a very large capacitor, you will expect that it will also have a large capacitance. So it's directly proportional to the area of the plates and inversely proportional to the distance between the plates. So for our next lesson, we will now go to the actual capacitor, which is a capacitor with a dielectric in between. So that's it for this lesson, and I will see you again next lesson.